Okay, so welcome to this video on linear programming. In math, programming is typically another word for optimization, and so another term for this topic is linear optimization. In general, if you give me any random function, not necessarily linear, and ask me to optimize it, find its optimal values, then that's in general a hard problem, and I wouldn't know how to do it. But for some specific classes of functions, this is a solved problem. And in particular for linear functions, this is a solved problem. We have something called the simplex algorithm, which allows us to find optimal values of our linear program, of our linear functions. And so we're going to discuss this topic with some videos. And so just to give you an example of what a linear program, in this first video I should just say that this video is going to be just about what a linear program is in general, and so I thought I'd give you an example just to see what we're working with. So let's try something. Here's we're going to minimize x1 minus 2x2 plus x4. So the x's represent the variable terms. And okay, so this is a linear function that we're trying to minimize, and there's many variables. There's 4 variables. Well, implicitly there's 4. You only see 3 of them, but the variables are labeled x1, x2, x4. So implicitly that means there's an x3 variable that just didn't appear in the function. So there's many variables, but it's still a linear function. It's a linear combination of those variables, and we're trying to minimize this. But we're not just trying to minimize it. It's typically a linear program comes with some constraints as well. So you're trying to find some variable values x1, x2, x3, and x4 that satisfy this, but that also, or that minimize this, but that also satisfy constraints. So here's some example of constraints that we might have. Maybe x1 minus x3 is less than or equal to 3, and x2 plus x4 is greater than or equal to 2. And maybe x1 plus x2 is exactly equal to 4, and maybe x2 and x3 are greater than or equal to 0. So that's an example of a linear program then, because we have a linear objective function. This function we're trying to minimize is called the objective function, and it's linear, and all the constraints are also linear. Maybe these bottom two look a bit different than the rest, but they're not. For instance, x2 being greater than or equal to 0, that's just another function. x2 can be viewed as a function, the function that takes the input x1, x2, x3, x4, and gives the output just x2. And similarly for x3. These are both obviously linear functions, and we have some constraint here. So this is a linear program. Everything's linear. Here is some things that could go wrong. For instance, what if we added another constraint? So let's just call this LP for linear program. What if we added some constraints? Here's an example of a constraint we might add. What if we added x2 plus x3 is strictly less than 3? Then this would no longer be a linear program. And it's because in linear programs we don't allow strict inequalities. Strict inequalities are not allowed, and so this constraint overall would not be allowed in our linear program. So if we did have this, it would not be a linear program. Basically, the reason that you don't allow for strict inequalities in linear programs is because you want everything to include their boundary points, so that everything is kind of closed and compact. Here's something else that could go wrong. What if instead of having this objective function, x1 minus 2x2 plus x4, what if instead we were trying to minimize 1 over x1? Well, then hopefully that should immediately be ringing alarm bells in your head, because this 1 over x1 is not linear. And so then we don't have a linear objective function, and so this would not be a linear program anymore, regardless of what else happened for the constraints. And here's a slightly more nuanced one, but still, what if we had the constraints x1 plus alpha x2 is less than or equal to 5, where alpha is a parameter that ranges, so we'll say for all alpha in the interval, closed interval 2 to 3. So that is to say we have constraints of this form for every alpha in the interval 2 to 3. So this would also not be a linear program. It's not because of the constraint, the less than or equal to. That's fine. It's not a strict inequality. It's because this alpha parameter has an infinite number of values it's ranging over. And so that would correspond to an infinite number of constraints here. And we don't allow for infinite numbers of constraints in our linear programs. Only finite numbers of constraints are allowed. And so this would not be allowed. So here we only have 1, 2, 3, 4, 5 constraints, which is a finite number of constraints. Okay, so just to recap, we have constraints have to be of the form less than or equal to, greater than or equal to, or exactly equal to. There has to be a finite number of these constraints, and everything, constraints and also the objective function, all have to be linear. And if you satisfy all those things, then what you have is a linear program. So here's the general format that we have then. We're either trying to minimize or maximize a linear objective function. So c1x1 plus c2x2 plus cnxn for however many variables there are. And so this is the x's are the variables, of course, and the c's are constant coefficients. We have a linear combination of the variables. And then there's going to be some constraints, so such that some constraints hold. And so let's say we have the constraints will typically come in a row. So here's a row that corresponds to a constraint. Go a row down, we have another constraint. Go another row down, we have another constraint. So however many rows there are, that's how many constraints there are. So let's index the coefficients, doubly indexed. a11x1 plus a12x2 plus etc. plus a1nxn. And then I'll put something here in a moment, but just let me explain this double indexing. For instance, a12, this 1, 2 index means this is the coefficient in the first row. Every row corresponds to a constraint, so this is the first row. Everything is in the first row right now, and the second index corresponds to the fact that it's the coefficient in front of the second variable, x2. So anyways, so I'll put a box here to indicate that either we'll fill the box in with either a less than or equal to, a greater than or equal to, or an exactly equal to, and then we'll say B1 is the bound. And we'll just do this for however many constraints there are. So here's another constraint. So it's now that we'll make the first index of the 2. So a21x1 plus a22x2 plus a2nxn, corresponding to the second row of constraints here. Then a box representing whatever we want to fill it in with, bounded by B2. And you do this for however many constraints there are. But we said there's only a finite number, so this will go up to m constraints for some finite number m. So a m1 x1 plus a m2 x2 plus a mn xn. There's some constraint bounded by bm. So I have m constraints, n variables, and that's the format. And all these a values are coefficients. All these b values are constant numbers that are the bounds. So this you can take to be the definition of a linear program. Something is a linear program if it can be written in this form. Where, let me just make the convention here, or not the convention, the just the fact that we need that a box corresponds to either a less than or equal to, a greater than or equal to, or an exactly equal to, like we've been saying this whole time. Yeah, and so if it's of this form, then it's a linear program. Okay, and so there's two more things that I want to mention then. Sorry, actually, we already mentioned the one. So there's things that can go wrong. We've already mentioned them, and that's what brought us here. The other thing that I wanted to mention, so there's really one thing I want to mention now, is that there's a more compact way to write all this, and that's with vectors and matrices. So if you're not familiar with vectors and matrices, you're not really going to be able to get very far with this, because in general, when you're doing algebra with linear programs, it's all done with vectors and matrices, not so much with individual values. So you're going to need to review that if you're not already familiar with this. But here's what we're going to do. Let me write over here to save some room. Let's take the vector x to be the vector that corresponds to the variables x1, x2, up to xn. So this is a variable vector with variable coefficients here. With variable components, I mean to say variable components here. Similarly, let's take the vector c to be the coefficients c1 up to cn. So c1, c2, up to cn. And so why is that helpful? Well, because now we can write this as, we're trying to minimize or maximize C transpose X. By convention, every vector is a column vector. So C transpose is a row vector. So a row vector times a column vector, that's just the dot product of two vectors. And so the dot product here, so what we have is C1x1 plus C2x2 plus CnXn. And that's exactly what we had up here, C1x1 plus C2x2. So this is just the dot product of the vectors C and X. Okay, and so, but you can see now that it's much more compactly written down here. And similarly, we can make the constraints more compact as well. Here's how you do that. Take the matrix A to consist of all the little a coefficients, and they come in the same order as they do here. So A will have the coefficients A11, A12 up to A1n, A21, A22 up to A2n, and so forth up to the mth row, AM1, AM2, AMn. And finally, we can take the vector B to consist of the components B1, B2 up to Bm, like that. And so the way we can write all this then is, we're trying to minimize or maximize C transpose X such that AX, A times X, big box B. And the way you read that, so this big box represents all the individual boxes for each row of the constraints. And the way you read that is, well, we know how matrix multiplication works. A times X, you take a row of A and multiply it by the vector X. So here's a row of A, A11, A12 up to A1n, and multiply it by X. And then you get A11 X1 plus A12 X2 plus A1n Xn, which is exactly what we have up here. And then a box corresponding to whatever the constraint is, and then the first component of B is B1, which is what we see here. And so we're just modeling this with vector notation, and now all of a sudden everything is more compact. So just to make sure we see exactly what's going on, let's just do this for this example that we had over here. What would everything be? Well, there's 4 variables, so we'll just do the example that we had here. X X is going to be x1, x2, x3, x4. There's 4 variable components. C is going to correspond to the coefficients in the objective function. So we have 1 x1 minus 2 x2, 0 x3, and 1 x4. So I have 1 minus 2, 0, 1. And then how about A? What would that be? So it's for all these constraints here. So I have 1 x1, 0 x2, minus 1 x3, and 0 x4. And then I have, I'll just make it like this. This will correspond to the big box, which is all the individual constraints. So here's a less than or equal to. And then B will be, the first component will be 3. So 1x1 minus 1x3. So x1 minus x3, which is what we see here, x1 minus x3 is less than or equal to 3. And then you just do that for all rows. So 0x1 plus 1x2 plus 0x3 plus 1x4 is greater than or equal to 2. 1x1, 1x2, 0, x3, 0, x4 is equal to 4. And you probably see how this goes at this point, but I'll just fill in the rest of it just to finish it off. Now we have x2 is greater than or equal to 0. So we have 0x1, 1x2, 0x3, and 0x4 is greater than or equal to 0. And you can just barely see that, huh? Let me move that over just a little bit. And then finally, the last one, 0x1, 0x2, 1x3, and 0x4 is greater than or equal to 0. And that's everything. So x is these 4 variable components, c is these 4 coefficients, and the matrix A is consisting of all these coefficients. Then we have this big box of constraints, greater than or equal to's, less than or equal to's, and exactly equal to's. We don't need to have all of those types. I'm just saying that those are the only types that we're allowed to have. There can't be any other types. And then finally the B is corresponds to these numbers here. And you see the 0 appearing twice because there's 2 separate constraints written here. Okay, but that's everything. So so again, and now that we know the X, the C, the A, and the B, we're able to write it in this format. And so really, this format is what you can take our definition of a linear program to be. If you can write it in this format, then it's a linear program. And this is going to be useful because when we want to show various properties of linear programs, it's good to have a concrete starting point, and then we can manipulate this starting point to get to other formats that a linear program might take on. There's certainly other formats for it. This is not the only one. This is just a good starting point definition. So in future videos, I think we'll see what other formats are useful for our purposes of proving properties about these linear programs. But for this video, that's it. So thanks for watching.